Okay, welcome back for another fun day. We are going to continue talking about magnetism. Last class period, we talked about magnetic force and magnetic materials. So I'm going to ask you a couple woo clap questions right off the bat about magnetic materials, and then we're going to talk about magnetic force on a moving charge. So our woo clap information so you can get connected up. Woohoo. One person in already. 2, 3.
I'm working on it. 10 minutes. Randy fixed a computer for me, and it's coming to it's delivered today.
Nice.
Woo! Praise the Lord.
Yeah, it's coming.
We have 8. Ms. Bauermeister says it's going to be a while before her computer connects, but we should have a 9th person.
It is a break.
Huh?
It is a break.
I have to do a little rain dance to make it work.
I mean, you can do that right now.
It's on the school Wi-Fi. I'm doing it, but this actually goes faster than the school Wi-Fi.
Okay, I will move on even though we have one besides Claudia that's still connecting. Magnetic materials, just a practical example, while Claudia's connecting, about magnetism. So I told you when I was a kid we had cassette tapes. You guys don't have experience with cassette tapes at all.
Yeah, it's not that.
Well, that makes me feel better. But what we often have very good experience with is a computer hard drive. Now, of course, we don't take them apart to see what's inside. But a computer hard drive is fundamentally the same thing as a cassette tape. The difference is the computer hard drive, you have a magnetic medium on a platen, a rotating disc, whereas on the cassette tape, you have the magnetic media on a piece of cellulose. Cellulose? Yeah. That runs through there. So what is going on with that magnetic media? You have essentially a goo. Oh, come on, right. You have essentially a goo, and inside of that goo, you have these little magnetic domains. So it's kind of like the picture I showed you of a piece of metal, but instead of those being in a metal, they're in this goo, which means that they can rotate fairly easily. And then to write either on your cassette tape or on your hard drive of your computer, you pass something over, see that thing that says read write head, and it creates a magnetic field that makes them so they either align like this or the other way. And so that's how it's writing ones and zeros. If they're aligned this way, that's a 1. If they're aligned this way, that's a 0. And then assuming that you don't bring a magnet close to the hard drive of your computer, they just stay that way. And then the read-write head will come over to read, and it will just sense, is this a north or a south magnetic field as it goes across, and that's how it reads it back. So it's a really ingenious way of storing memory. How many people know what a core dump is on a computer? A core dump? It used to be whenever your computer crashed, it would say core dump, and it would sit there for like 5 minutes. And you'd be like, what in the world? Well, it's because before they had things like a hard drive, they developed other kinds of memory. Things like punching holes in a car. Or making little pieces of magnetically soft metal, like little iron cores, and then they put wires wrapped around them that they could use to magnetize them. And so the core dump was actually going through and reading the memory in those magnetic cores. And they maintained the term core dump means reading the memory and saving it so you can actually restart the computer in the same state it was when it crashed. So the idea of the core dump is so you don't lose information when it crashes. Okay, now hopefully, yep, all 10 people are in. Question number 1. Which kind of magnetism is always present? These are the 3 types of magnetism. There's no distractor. All right, 9 out of 10 have answered.
That's stuff from yesterday. I get so confused with my notes.
All right, everyone's answered. We had 5 people that said diamagnetism, 4 who said ferromagnetism, 0 who said paramagnetism, and I had there an option none of the above, and 1 person said none of the above. So we have no simple majority, but we do have a plurality, and they're correct. Diamagnetism is essentially anti-magnetism. We learned that, well, what we learned was if I have 2 norths, they'll oppose. If I have a north and south, they'll attract. Ferromagnetism, if I bring a magnet close, it's going to react strongly. They're going to orient so that it's attractive. Diamagnetism, if I bring it closely, it's going to react weakly and orient so it's repelled. Paramagnetism, it will react weakly and attract. So those were the 3 different options. They all have to do with magnetic materials aligning, and diamagnetism aligns to be repulsive. And this is present in all materials. But weaker than the other 2. So you don't see its effect unless it's not ferromagnetic or paramagnetic because it's so weak. All right, any questions about that? Next question. What kind of magnetism is strongest? And Ms. Bauermeister's got this. Nine, 10, everybody answered, and everybody answered correctly. Ferromagnetism, the kind of magnetism you see in iron, is the strong kind. And then our final question, what type of magnetism is always repulsive?
Isn't ferromagnetism and other things too?
Excuse me?
Isn't ferromagnetism and other things too?
Besides iron, yes. Break the tie, last person. Break the tie. Last person broke the tie in the wrong way. Always repulsive. Go back 2 slides. Repulsive. Diamagnetism is always repulsive. What we had for our answers was 4, 1, and 5. Paramagnetism is attractive, but it's weak. Ferromagnetism is attractive, but strong. Diamagnetism is repulsive. And all of these are for the case where you bring a magnet close to the material. Now, I started on magnetism by showing how magnets interact with other magnets, how north attracts south, and talked about there being no magnetic monopoles, that you have to always have the north with the south, so everything behaves like the little bar magnet. We, in this class, do not at any point actually talk about the force between 2 magnets in terms of calculation. We talked about it existing and the rules: opposites attract, likes repel. But when we talk about force, which by now you know is a really important thing in physics, we're always going to talk about the force on a charged particle due to magnetism. So our magnetic forces are going to be on charged particles, not on magnets. And we start with the law. The magnetic force is QV. How should I pronounce this?
Cross product.
I should pronounce that cross. Why not times?
Because it's perpendicular.
Okay? It's not times because you can't multiply vectors. You either do a dot product where you multiply the parallel parts, or you do a cross product where, as David said, you multiply the perpendicular parts. That's why it's got a cross. So the two signs that normally mean multiplication, dot and cross, mean different things if you have vectors. So despite Sarah's challenge to watch her show how to multiply two vectors, you can only do a cross product or a dot product, and the cross product is multiplying perpendicular parts. We saw cross products last semester in the context of torques. So in talking about the cross product, technically this is review. In practice, you're very rusty, so I need to spend some time with it. So when you're going to find the magnetic force on a charge, now notice it's QV cross B. If the particle is stationary, then what is the force on it due to a magnet? Stationary, that means the vector velocity is 0, right?
Yeah.
And so what would the force be on a, let's say, an electron in a constant magnetic field?
It should be 0 for both.
It's 0 because you have 0 for the velocity part. So some places, like on the first slide, the title was magnetic force on a moving charge. Because a stationary charge is not there. There's no V. Okay, so to calculate the magnitude, and as I've been saying for everything this semester, calculate the magnitude and direction separately. With the cross product, you really have no choice. You have to do them separately. So you calculate the magnitude. The magnetic force is QVB times sine of the angle between the two vectors. So the sine of the angle between V and B. So now that brings up another interesting thing. What if the velocity is parallel to the magnetic field? Like, for instance, the Earth's magnetic field is pointing roughly north, right? And so if I have an electron that's traveling north, what can you tell me about the magnetic force on it? And I said it's traveling north.
Right. But the magnetic force, because the stuff whole magnetic would be the same before. Wait, I'm sorry, maybe I'm confused.
You're thinking about a different thing than the actual. If you have a magnetic field that's north and you have a velocity that's north, what's the force on that moving part of it? They're parallel.
Right. So
So the perpendicular parts are 0.
right.
Because theta is 0, so sine of 0 is 0. So if you have motion that's parallel to the magnetic field, it doesn't matter what the charge is, it's going to have 0 force. Yes?
Is this a stupid question, but can you define the variables?
Yes. Q is charge, V is velocity, and B is the new one for us. That's the magnetic field. And I forgot. In my mind, B is magnetic field, and but there's no B in magnetism, right? You might ask, why don't we use M? Well, M is used for a special variation of the magnetic field. So you have M, B, and H. B is the variant that we use in general physics. So that I forgot to verify or to explain. Yes. So B is the magnetic field, and it's a vector. It has a direction. Points out of north into south, always does loops. So we have the right-hand rule, and there's multiple ways of explaining the right-hand rule. I put here a picture, I think it's from Wikipedia, of the standard right-hand rule explanation. If you have A cross B, you take your right hand, you point your index finger in the direction of A, orient your hand so your middle finger can point in the direction of B, and your thumb points in the direction of A cross B.
And B is always going to be perpendicular to A.
Those are just random variables for cross product. No, they're not always going to be perpendicular. So if, let's say, A is this direction and B is this direction, those are not perpendicular, right?
That's true.
So sine of the angle for the magnitude, sine of the angle between them, and then I would have A cross B, and my finger just goes to that direction. So if it was like this, I would have to orient my hand like this.
Okay.
The other way you commonly see is start with a straight hand pointing in the direction of the first vector, and then orient your palm So your fingers are still pointing in the direction of the A vector, but they can then bend toward the direction of the B vector. And it has to be on the palm side. You can't make it so you hyperextend it back this way, or so you curl more than parallel to the hand. So either one will work, and we will practice a little bit. A lot of it. Notice the middle line here. What does it mean if you have the vertical lines on either side of A cross B? Okay, absolute value, which with vectors means magnitude. It's still absolute value. That's why it's the same sign. So the size of the vector, its magnitude, you can put as A cross B is the same as B cross A for magnitude. And that's the component of A perpendicular to B times B, or the component of B perpendicular to A times A. Either way will get you the same answer. And or AB sine theta, which is what we usually just jump to. Because A sine theta is the component of A perpendicular to B, or B sine theta is the component of B perpendicular to A. So it comes out. But the bottom line is an important thing. If you reverse the A and B order, while the magnitude stays the same, the direction reverses. So B cross A is the opposite direction as A cross B. So remember, minus north is south. That's basically what it's saying. So when we do these cross products, it's really important to keep the order straight. If you reverse the order, you reversed your direction. Now the units for magnetic field. So B is magnetic field. It's a vector, so we have an arrow over it. If you just look at this equation, all the way back here, if I solve this equation, the magnitude equation for magnetic field, I would have B is equal to the magnetic force over QV sine theta. And so in terms of units, and this is real simple, you can all do this along with me. What is the unit for force? I say this is all simple. You know that almost everybody in life wouldn't be able to answer that question. What is the unit for Q, the charge? Coulombs. What is the unit for V, the speed?
Meters per second.
Minutes per second. Absolutely. So the unit for magnetic field must be a Newton per Coulomb times meter per second. You can rearrange that a little. Newton over Coulomb per second times meter. And what's a Coulomb per second? So you could write that as Newton over amp times meter as well. These are all defined as the Tesla. So the standard unit for magnetic field, just like we had Newton for force, joule for energy, for magnetic field, it's the Tesla, with 1 Tesla being 1 Newton per amp meter. And you notice we don't put MA, because if you put MA, it'd be milliamp. And in fact, the dot is there just to make sure you don't get them confused and think that they're part of one thing. If you put M dot A, it would be clear that it's a meter times an amp. It's just better to put amp times meter to avoid confusion. So that's our standard unit for magnetic field, the Tesla, named after Nikola Tesla, who you probably have heard about. Pretty amazing dude. Came up with lots of really great discoveries, had a brave battle with Edison, and Edison won. And so we have alternating current for our electricity. I tend to think that in hindsight that Edison had the better option here. But a lot of people side with, the DC option. Well, I think it was DC. I don't know. The option that Nikola Tesla had would have been better. It was a wireless method, which basically meant everywhere you walk, you'd be in incredibly strong electromagnetic radiation, which these days a lot of people are worried about their cell phone radiation. Yeah, it would be a lot more. Another common unit that you see for magnetism, for magnetic fields, is the Gauss. And I'm always really clear. We pronounce this word Gauss. It was Carl Friedrich Gauss's last name, not Gauss. And 1 Gauss is simply 1/10,000th of a Tesla, or 10,000 Gauss is 1 Tesla. So it's a very simple conversion between the two. Why do we use the Gauss? Well, the Earth's magnetic field is about 0.5 Gauss. It's a convenient unit for typical sizes of magnetic fields. Whereas the Tesla, magnetic field of 1 Tesla is really large. Just like a charge of 1 Coulomb is really large. And so we often count charges in electron charges because those are more typical. Well, in chemistry they are. One last thing, just notation. We haven't dealt much with in and out. We've dealt with 2 dimensions. But when we're dealing with magnetism, we are inherently going to be doing things in 3 dimensions. And so when we draw diagrams to show in and out of a page, we have, the idea is an arrow. I should just get an arrow, maybe for next year. So if you have an arrow and I point the arrow at you, you see the tip of the arrow, right? There's the dot. And so that's what coming out toward you is supposed to be, is the tip of the arrow pointing at you. Whereas if I'm here and I'm shooting the arrow, I see the back of the arrow and I see the fletching, the feathers. And so that's what this is supposed to be, is the feathers of the arrow if it's going away from you. I give you the reason why those mean what they do so it can help you remember it better. Yes, Ms. Bauermeister.
Are you going to show us an example of these and like when you will see them?
We will see them often in the coming weeks, yes. Yes, they won't be just a one and done. How do we solve problems? We solve problems first. Check to see if the magnetic force is 0. Right, if the magnetic force is 0, you're pretty much done, right? And so there's 3 cases here that would give you magnetic force is 0. If the particle is not moving, if the particle is perpendicular, if the particle is not perpendicular to the magnetic field, that its velocity is parallel to it, or if the magnetic field is 0. I left off one because it says point charge. If you had no charge, that would be 0 as well, but then it wouldn't be a point charge. So that's another thing I'm supposed to check. Make sure you have a charged particle. Then we're ready to actually start doing some work if it turns out there is a force. So determine the angle between the velocity and magnetic field. Because we're going to calculate the magnitude separately from the direction. You don't have a choice here. Well, I guess we'd be using a matrix taking a determinant. So determine that angle, then calculate the magnitude using this equation. Notice, put an absolute value on the charge Q. We're just calculating the magnitude. So I put the magnitude of the charge. We'll get a positive number, and then we're going to apply its direction using the right-hand rule. So you then finally determine the direction of V cross B using the right-hand rule. And remember that if it's a negative charge, the direction of the force is going to be negative in the direction you got from the right-hand rule. So that's our method. With that method in mind, let's do some problems. What do you say? Yeah, sure. Okay, first we'll answer 3 woo clap questions. Question 1. A positive charge travels east, so the velocity is like this, in a region where the magnetic field points down, so the magnetic field is like this. What direction is the force from the charge? I'll even write the equation for those who don't have it.
Just a side note. Is it possible to make time on Friday? Because if not, I'll just try to make it with you on my own. But I think the equation sheet is still a little confusing, to me at least. Is it possible to take 10 minutes on Friday to go over and come up with strategies of the class on how to use it on the test?
Sure, I can do that.
How do you know what A and B?
A was a fill-in variable for the first thing in the cross product. B was a fill-in variable for the second, right? It was A cross B, now it's V cross capital B.
So is the first thing supposed to be piece with respect
Okay,
to the
whatever is first in the cross product is the first thing. So come on, show up. Oh, right. So this here is the first thing in the cross product, and this is the second thing in the cross product. Okay, we've gone 2 minutes and we only have 6 answers. I'm just going to stop it here and we will work it through together because, you know, we're having some difficulty with this, which is fine. Oops, I skipped the line. Okay, so we had, what was that? You know, does, oh, yeah, it does say 1 on south. I missed that. 3, yeah, that comes to 6. We had 6 people. 1 person came in at the last second. I'm not saying it to you, saying I missed it when I wrote it down. So let's just go through this. Let's have Max lead us through. So Max, force is QB cross B. So if we're going to apply the right-hand rule, what's the first step?
Finger pressing pointing.
Okay. Index finger
East has pointing toward east, right?
needs to be pointing the direction of the velocity. So since the velocity is east, index finger needs to be pointing east. And of course, remember, it needs to be the right hand. Everyone has the right hand, just making sure we don't forget that. Oh, everyone's on. I didn't notice.
Doesn't the magnetic field be pointed at second
Okay.
with the middle finger?
So the middle finger needs to be the direction of the magnetic field. So I need to rotate my hand so I can point my middle finger down. And then what direction is my thumb pointing? North.
I was only halfway close.
He's used to this with the. Okay, so we're going to go through and do a couple more examples here. Any questions on this? I just worry you're going to drop it on the ground. Okay, so a negative charge, notice a change, it's now a negative charge. Travels east in a region where the magnetic field points down. What direction is the force of the charge?
Thank you.
Okay, we have 9 answers. Okay, 10th one didn't get in. We had 1 and 8. 8 people said south, 1 said no force. Somebody who said south, why did you say south? I don't know.
Because the other one was north.
Because it's a negative charge, so you have to reverse it.
Okay, it's the same right-hand rule. And so your thumb's going to point north. But because it's a negative charge, we have to reverse it to south. So it's important to pay attention to the charge. You don't just do the cross product because you have the charge multiplied by that cross product. All right, last woo clap question. A positive charge travels down in a region where the magnetic field points down. What direction is the force in the charge?
Oh.
Righto, you two. Righto, Don Pardo.
So it's going to go down. And then they went down. There's two.
That was my worry.
It's okay. It's still up.
It's still edible. Not in my book, it's not.
It was.
Okay, we only have 6 answers still. Is it still edible?
That's still edible until it goes to the one down.
Okay,
Well, it's still.
we only had 7 people answer. 3 people are completely lost, so we need to make sure this is clear.
Yes, it's clear.
We had the equation was,
They always say that. They'll explain something and they'll be like, cool, clear as mud, and we'll say yes. And then that means it's explained.
really,
They said it a lot.
because clear as mud obviously means the opposite.
Well, that's the joke.
That's the joke. Okay, so this is our equation. Force equal to Q V cross B. Cross product, as David said, means the perpendicular parts. So when we did the magnitude of the force, that was equal to the magnitude of Q times VB sine of the angle between the two. Well, if they're both down, then theta is 0, and sine of 0 is 0. So you could either say, the equation says sine 0 is 0, so the answer is 0. Or you could say there's no perpendicular parts, so the answer is 0. David?
What if it was going up instead of down?
What if it was going up instead of down? What sine of 180 degrees? 0.
So it's still parallel?
Yeah.
Even though they're going in opposite directions?
There's no perpendicular part. Remember, we're multiplying perpendicular parts. Opposite direction is still not any perpendicular part.
Okay, so the perpendicular part means anything between 0 and 180.
Yeah.
So if it's at 1 or 150, 1.
Yeah, there would be a component.
So long as it's not on that straight line.
Yeah.
Okay.
But then you multiply by sine of the angle to find what the magnitude is.
Right.
Okay, so any questions now on these 3 different examples?
Can we do another example?
Excuse me?
Can we do another example?
We will do practical examples now. Solving a problem. I'm going to do the first problem, then you're going to do the second one. And the second one is like the first, but it adds a few wrinkles. Of course. So suppose a proton is moving straight down directly toward the equator at a speed of 468 kilometers per second, because that's how fast the solar wind is hitting the Earth. What is the magnetic force, both magnitude and direction, on the proton due to the Earth's field? So here I have a diagram. Here's the velocity that's going straight down and the magnetic field that's north. Let's start with the first easy thing. First thing was determine if the force is 0. Case number 1 was if velocity was 0. No, 468 kilometers per second, and not 0. Case number 2 was if they're parallel to each other. These are perpendicular.
Wait, I'm confused how you even figured that out.
How I figured out what?
That it's going down and north.
That was given in the problem. So I just read the words. Well, actually, the north wasn't given in the problem, but the picture showed the magnetic field going north. Okay, so
is the magnetic field always going north like that?
well, here's this diagram is showing the magnetic field in close proximity to the Earth, and as long as you are reasonably equatorial, yes. Now you say always, it's complicated. The sun interferes with our magnetic field because of those charged particles flying from the sun, the solar wind, the ones we're talking about here.
Right.
And so they cause it to deform, so it will smash a little bit closer, making the magnetic field stronger, on the side close to the sun and stretch out, just like with electric fields, the lines are farther apart, they're weaker, making it weaker on the other side and changing the direction somewhat. And so we have a diurnal variation in magnetic field. Your compass actually will change the direction it points a little bit throughout the day because of the sun's effect on the magnetic field. We also have an annular deviation based on the rotation unit. It's complicated. For our purposes in general physics, it's always pointing north and may dip into the Earth or come out of the Earth if you're in the southern hemisphere. Okay, so question number 1 was the magnetic force magnitude and direction? We're going to answer direction first. So I have Magnetic field and the velocity, write our equation here and what's going to turn out to be pretty much microfiche. Microfiche. We used to have to go look up articles on microfiche when I was your age. They take pictures of stuff and print it in a really small film, and then you put it in a film reader.
Oh, yeah.
Okay.
You're saying microfiche, but saying fish weed. It's like, I don't understand.
That's what I thought too.
Well, it's FICHE. Okay, so, or we could just say microfilm and be done with it.
Okay.
Force is QV cross B. Is Q positive or negative? Positive. Okay, so that's an important thing to recognize. That means my answer for direction is going to be the same direction as the answer for the cross product. If it was negative, it would have been the opposite direction. Then I have V cross B. So V pointing down, B pointing north. And I'm just using, I'm looking at my picture, which is opposite to yours because of the direction. So V is this direction, then B is up. So my thumb is pointing into the screen. So I'm going to make that. How do I show into the screen?
With the cross. Yeah, that.
So that's the direction of the force vector. Now, based on this, north is up, south is down. Here's a picture of the Earth. What direction is going away from us in this picture?
This one?
North, south, east, west.
East is going away.
East. So that is pointing east. I'm north, south, west, east.
I don't know. I don't know. Wait, you're saying that this going into that
Here-
is east? Yes.
Here's looking down on the surface of the Earth.
Yeah, okay. It's my east. Here. This way is my east. Or this way is that east.
East is that way.
Not right there.
Oh, I thought you were talking about physical here Lincoln in our classroom orientation. I'm so sorry about that. So, east is the direction that the Earth is rotating toward, and so east is going. It depends on where you are, right? But east is going that way. So on that side, east would be. Okay, so we have the direction. Now we need to calculate the magnitude. So the magnitude of the force is Q VB sine theta. Charge of a proton, 1.602 times 10 to the minus 19 coulombs. The speed, 468 kilometers per second is 4.68 times 10 to the fifth meters per second. And we want it in SI units.
Wait. Oh, wait. Protons. Okay.
And then the magnetic field is 0.5 Gauss. How many Tesla is 0.5 Gauss?
No. 0.5 house. That's going to be very low.
Yes. It's like
1 Gauss is 10 to the minus 4 Tesla.
So it's going to be 10 to the minus 8.
I'm not sure where the 8 came from. We have half of 10 to the minus 4 is 0.5 times 10 to the minus 4 or 5 times 10 to the minus 5. So we multiply that all together in our calculator. And somebody want to punch that up real quick? I did do it before class, but I don't remember what the answer was.
Okay, so the Q is the cardinal proton.
Mhm.
The V is the 1.6.
The velocity of that proton.
And then the E is the electric field.
Magnetic.
Magnetic field.
Yes.
But it was on the time data.
Oh, yes. Let me put sine times sine of 90 degrees.
It's not going to be easy.
Right.
Okay. So I got 3.749 times 10 to the negative 8. I don't think it-
Okay, now I only put 2 sig figs because we only had 1 sig fig in our original number. So this is the magnitude of the force, and its direction is east. So my force vector is equal to 3.7 times 10 to the minus 18 newtons east. Now, based on this, can you understand how Earth's magnetic field is beneficial to us? We're about to get that answer. We have charged particles flying at us from the sun constantly, if you're on the side facing the sun. But the Earth's magnetic field, if it's a positive charge, it's going to deflect it to the east. If it's a negative charge, it's going to deflect it to the west. So these charged particles don't hit us. So we're protected from that radiation. Where are we not so protected? Looking at the picture. At the poles, because at the poles, it's not perpendicular. So if you have that same charged particle, the same direction coming in here, it loops around that magnetic field line and comes into the pole. And so we have charged particles that are coming into the Earth in this region here. Hence, aurora borealis and aurora australis. The aurorae occur at the polar regions because that's where the charged particles are coming into the atmosphere. Just on a side note, you know I'm a creationist, right? If I believed in evolution, I would definitely propose that it's a punctuated evolution with a lot of genetic change occurring when the Earth's magnetic field switches. Because when Earth's magnetic field switches, we're going to go through a time period where we don't have the magnetosphere. We're not going to be protected from this radiation. And thus we'll have a lot of what we call ionizing radiation, we'll learn about that later, that would be hitting all of the things on Earth. And one of the problems with ionizing radiation is genetic mutations can be caused by it. Okay, now it's your turn. Look, I did it all on one page.
Can you go back?
Where on Earth is the shielding least effective? At the poles. At the poles because it's not perpendicular. Okay, so your turn. At a certain place, Earth's magnetic field has a magnitude of, it's the same magnitude. I just put it now in milliteslas instead of in Gauss, but it's the same number, 5 times 10 to the minus 5th Teslas.
Oh, it is?
Yeah. But the direction is 70 degrees below horizontal. So it's not like this, it's like this. With compasses, we actually usually use 2 compasses. One, a dip compass to measure the angle going down to the Earth. So use that one to get the direction of the magnetic field horizontally. This one here, by the way, it doesn't really work. It's not balanced right. But then you put this one, so it's pointing the same direction as that one's north, and measure the angle it dips. I didn't understand the question.
Yeah, which direction is it moving?
Oh, yes, moving due, let me zoom out a little bit, east. Thank you. Moving due east at 250 meters per second. That's a good plan. So choose a 2-dimensional configuration, either north, south, east, west, or north, south, up, down, and then use the dot and the X for indicating the other 2 directions in your picture. And since we have east and north and down, kind of have to choose. What you would like to see on your picture is the angle between your velocity and the magnetic field.
So it wants to figure out the direction.
this.
Yeah, and this is one of the most little horizontal. The horizontal is point to more. So one of those is just where magnetic.
Right.
I'm definitely open to
Yeah.
So if I will, if I draw north, south, up, down. So not for what I want to illustrate. In solving the problem myself, I would draw two pictures, one with this and one with the other. So in drawing north, south, up, down, my magnetic field in this case is pointing in that direction, 70 degrees. And then if I draw north, south, east, west, my magnetic field in this picture would be looking like that. And my velocity, if I draw my velocities, in this picture, my velocity is going like this. In this picture, the velocity is got to make sure I get this straight again. Here's up, there's north, and so east is that way. It's a three-dimensional picture. If you look in the plane of the velocity magnetic field, which is the plane you need to think about for the angle, they're right angles. Because the velocity is straight east, and the magnetic field is 9 degrees below, or 7 degrees, below north. And so if you just look at the angle between those two, it's still 9 degrees. My hands didn't do it, yes, but it's 9 degrees.
Can you scroll back up, please?
Yes, I just want to make sure we got the picture straight.
And how do you determine the charge of the ion?
It has a charge of -1 because it has a single minus there. It's a good question because, we're not in chemistry class, we're maybe not used to the nomenclature, but that means that it has a charge of -e.
Okay, so electron.
It has the charge of an electron,
Okay.
not the mass of an electron.
Right, the charge. Okay.
So I would just say that P is pointing due north because it says due north, pointing due north.
The velocity is due east. I'm not sure.
Is this a horizontal points due north? East?
Yes. So the magnetic field is pointing like this, right? The horizontal component is due north, and then also has a downward component.
Wait, why does theta equal 90 instead of 70?
It doesn't.
Theta is 90 degrees because you have your magnetic field is like this.
Yeah.
The velocity is like this. The angle between those two is 90 degrees.
Wait,
So what is
so what is the 70 even for?
That's telling us the angle that it's dipping, and it's going to be important for determining the direction of the resulting force.
I didn't use that in this stuff.
You don't use it in finding the magnitude, you use it in finding, well,
That's not.
yeah, it's in part of the direction, because your direction, you have D like this, cross B like that, and so it's pointing down into the south.
Oh, wait, no, it's, no.
I can do that, but I can't do that. So it's like 70 degrees below the part here, right?
That's correct.
Okay, and the other part's going this way.
And what?
The other part's going east, which is.
Why wouldn't it be?
Well,
30?
the first one is north and down. and the second one is east.
North and down. How can you be north and down? You're north up.
Up is this way, north is that way. They're perpendicular to each other. Three-dimensional. We're doing a three-dimensional world here. It's harder. It's harder. Okay, we're out of time. We will finish at the beginning of next class period, okay?
Are we gonna have homework questions on this stuff? Maybe.
Yeah.
Did you finish?
I'll be prepared to ask the answer. The other